It's okay? Okay. Okay, so yeah, just let me check if it's working good. I think we stopped here last time, right? Okay, so do you remember what we said about this this slide, and what was the conclusion? Do you remember? Sometimes just by changing illumination, so you make the recognition very sensitive. You know, you make it sensitive to recognition. So this is what we said last time, and here look at this slide. Still in face biometrics, and the idea here, you know, when you use face recognition systems, the idea is that different algorithms used to recognize people, including, you know, for identification or verification, you have to understand that the performances of systems are sensitive to many things. We saw last time, okay, the problem of elimination, but we can also say that the face recognition algorithms can be sensitive to the expression, you know, and emotion. Here you have just some examples of some faces, you know, to the same person. You can notice the same person with different expressions and emotions. So if you use any recognition system, in some cases, maybe your system will not recognize the person, basically because the expression changed. So can you understand why it becomes sensitive in such a case? Why sometimes the parameters will change. In fact, if I take, for example, here a whiteboard, and just I try to, let's try to consider two situations. Maybe this one is smiling, okay? We call this smile. This is the same person, and this is neutral, okay? We call this neutral situation. Here it's smiling, and maybe we can take another configuration with I don't know, sad. Okay, so probably yeah, you took a class maybe with Elam about some applications, you know, to recognize faces, to extract features, and even now you are taking some classes to extract features from faces. So one of the approaches, especially local approaches, consists in extracting some features, some specific features from the faces. So you saw some methods, you know, where we have to extract some points or landmarks, if you want. Okay, so we can extract here some points from the eyes, and you can, yeah, maybe let me change the color, maybe it's better in red. And you extract here for the nose some points, and even here for the mouth you saw that we have to use some points, you know. Okay, so this is the person A, and it's in fact the same person. The only difference is that here the person is smiling, here it's neutral. So if we by changing the expression, okay, we have the shape of the face. Maybe the shape of the face here is exactly the same as this one, but the problem is that when this person is smiling, we may face some modifications, especially here at the level of the mouth, you know. If you measure this distance and this distance, it's not the same. Maybe at the level of the eyes, maybe you can have some modifications, things like that. If you do the same measurement over this face, so even if the face shape will be the same, so probably here it will be different. Okay, so features here, features from different faces will change slightly depending on the expression. Okay, depending on the expression, features will change. So here, you know, when you extract features, very often these features are stored in vectors. Remember, I will try to. So x1, x2, x3 until xn. So all the features are stored in one vector, and we do the same thing with this second expression, and it will be another signature. So maybe this one I will call it y, and the other one here I will call it y2. Okay, so this one is y1, this one is y2, and from this one we will obtain a vector y3. Okay, so maybe the features here for the face are the same, but locally some features will differ. So when you use the face recognition system, you know, it's about matching, especially for verification. You have to match the data to the data stored in your database. If there are some differences in terms of, you know, because the person is smiling, because the person is sad or something like this, so maybe the person will not be recognized. Okay, that's why very often, you know, face recognition systems are sensitive to this. So when you develop your own algorithm, you can try to make the system robust. Okay, you can try to make it robust regarding expressions. What does it mean when we say I developed an algorithm robust to expressions. What does it mean? Yeah, it means whatever is the expression, or even if the person is smiling or sad, so the recognition or performances of recognition will not really change, and we say it's robust. And here it depends on the algorithm. Some algorithms are sensitive to slight variations. Some other algorithms are less sensitive. So it depends on the way. Pardon? It depends on the way you train your system, it's for sure, because if you train your system so that you say, this person, you can meet this person in this situation, for example, smiling, expression, or sad, here, yes, we can make your system robust, okay, in the training. So in the training, you will use as input different situations of the same face. So you use a training and you say, this is the same person, even if you have some modifications in the features. Here you may create something a little bit robust, okay? Otherwise, your system will consider each situation, each expression as specific person. If you compare just directly features extracted from the enrollment to a specific situation, just matching one-to-one, here it may be an issue, okay? That's why it's important. In some cases, you can use an intelligent system, you can train it, and you can say, okay, here, this is the same system, the same person with different expressions. So robustness is very important. Always you have to think about this. If you create a face recognition system which is very sensitive to variations, a system which is not robust to variations, here it may be a big issue. It may be a big issue, especially for faces, you know. Very often, you know, we can meet someone who is happy, sad, smiling, and you know, sometimes it's very, very difficult, you know, to have exactly the same features. That's why think about robustness. Each time you develop an algorithm, and especially people who will work in research, and even for, you know, for the industry, you develop your algorithm. In your report, people, they will say you, okay, can you just tell us about the performances of your system? Okay, performances of your system. And when we talk about performances about your system, so probably you will take some classes about evaluation of performances. The idea is that, is your system robust? In other words, is it sensitive to some special conditions? And among these conditions, we can talk about, of course, elimination. This is what we said last time. And here we talk about expression. So normally when you have your curves, okay, of performances, and you will see in the future, you will take some classes about how to evaluate performances of your systems, especially by considering the false acceptance rate and, tell me, false rejection rate. okay, which is very important. This curve may change depending on different situations. So this is very important to highlight the sensitivity of your system if you have if the elimination conditions change or if expression conditions change. And you can meet some other conditions, like what? Occlusion. What is occlusion? Pardon? Yes. Okay, here, the example you have here, it's just a problem of, elimination issue. You know, the same face captured in different situations. Okay? So, do you imagine if you use some global recognition method? It's exactly the same person, but if you try to extract features, it's for sure you can try to do it, extract features from this face and from this face, and you will see the difference, or from this one, or this one. So that's why it's important to take into account, you know, elimination issues. Yes, before talking about occlusion, there is another problem that you can meet. We call this pose issues. Pose issues. So you can see here the same person, which is in front of the camera. And you can understand if you want to extract some features from this face, it's easy to do. Why? Because the person is in front of the camera, the elimination is perfect, okay, and here you can extract, you know, I don't know if we can do a zoom, but at least we can extract features from the, at least we can have the shape of the face, we can extract some features from the eyes, nose, and mouth, okay? And we store all these features in a vector x1, or I call it y1, with all the different features. Now you can see this situation where the person is not looking at the camera, but direction is different. So if you try to use the same algorithm, okay, you have an algorithm to extract some features, and you want to apply it here, be sure that you will extract another vector y2, which is completely different than, maybe not completely, but you will see that it will be different compared to the first one. So depending on the, you know, the angle of the pose. So the angle here and here or here, it's not the same. And if the person is looking, you know, from the profile, and if you try to extract features from this face and you compare it to this one, you understand it's not the same. So we call this pose issue because in some situations, especially if we call this uncontrolled situations or uncontrolled environment, you know, you have to make a difference between controlled environment and uncontrolled environment. In the case of controlled environment, you have your face recognition system equipped by a camera. Okay, this is a camera. So very often, when the system is controlled, you will ask the person or the user to look at the camera in front. Yes, and you say, don't smile. don't move, don't do this, don't do this. And we try to control the light, the illumination. And here you are in, it's a controlled. Pardon?
For example, when you are in a passport office.
Yeah, sure. Yeah, for your passport, for in many situations, we prefer to control the capture, and we can understand this. Why they do this? Just to have, to reduce, to minimize all the different constraints due or related to illumination, pose, and so on. So you ask the person to be in front of the camera. You ask her to be neutral without expression. You control the illumination. What else? What can we control? Environment. Or sometimes we use the term supervised environment, either controlled or supervised environment. So here, what else excluding the illumination? We talk about illumination, about the pose, expression. What can we ask?
Maybe occlusion, maybe the hair.
Yes. Occlusion, we will talk about occlusion, but here even we can say if the person is maybe wearing glasses or using, I don't know, a scarf or something like this for occlusion, we say, no. You have to remove this, you have to remove this, you have to remove this, and so on. So here, if you use an appropriate face recognition algorithm, if you have good illumination and everything is okay, normally you can get good performances. Okay, so you have this situation in a controlled or supervised situation, and in some cases you have uncontrolled or unsupervised situations. And here it's basically, if we want to identify people, because here sometimes we can use this system for verification, for example, and you have collaboration between the user and we would like to say the authority or the person who is using the system, who needs to use the system. In some cases we don't ask permissions for people. We have a video surveillance camera. Okay, you have a camera and you have a lot of people moving, for example in metro station or something like this. They are moving, but of course these people are walking. You cannot ask them, look at the camera, take off your I don't know, the scarf or the glasses or something like this. So here it's a very difficult problem, because you will face problem of pose. It's for sure. Why? Because people, they will not look at your camera, and even in some cases they don't know that there is a camera. You cannot tell them, take off your glasses, take off this. You cannot tell them, don't talk, don't smile, don't do this. It's impossible. So this is what we call an uncontrolled or unsupervised situation. And here, the algorithm that you have to use, it's up to you. It's up to you to make an effort for the identification. You cannot ask users to make an effort. It's your problem, it's not their problem. Okay? So this thing is very important. And each time as I said, when you develop an algorithm, face recognition algorithm, and when you want to publish your results, people, they will ask you to publish your performances. You have to evaluate the performances of your system. So here you can say, okay, let's evaluating the performances of our system in this condition, controlled or supervised environment. Or let's evaluate performances of our system in uncontrolled or unsupervised condition. Okay? So we thought, yeah, about the occlusion. Now we have some slides. So here you have some situations of occlusion. Okay? Glasses. Here, yeah, here we can say, yeah, maybe the beard. Okay, the beard here is a part of occlusion. Here you have the scarf. Okay, so why do you think that it may affect performances of your system?
Because we lose some features like marker and we can't see.
Yes, you may lose some information. So if you take, for example, this one. Okay, you extract some features. You use the shape of the face, shape of the eyes, nose, mouth. Okay, and here you store this in a signature vector. You will use it as signature. So if you have something like this here, you have the beard here. The problem is that, okay, this one is not. It's easy maybe, but in some cases you can have, I don't know, beard like this, and it becomes an issue. Why? Because when you want to detect the shape of the face, yeah, it's completely hidden and you cannot have the shape of the face. Okay? So maybe you can access to the information here, the eyes, nose, okay? But you will lose information here. So your signature vector will be sensitive. You will lose one part. Okay? Here it's the same, because if you consider that your signature vector, okay, I call it Y, and you have one part for the face shape, another part for the eyes, another part for the nose, and here you have the mouth. So maybe here you have 10 or 20 points. Here you have 10 landmarks. Here the same, and so on. So if you hide one part of the vector, for example, here you cannot extract the shape of the face, it means you will lose this part. So maybe you can, by this occlusion, you can lose 20% of the information. If you are in this situation, maybe you can, because here you cannot use the eyes features, so you will lose maybe 10% or something like this. And do we imagine if the person is hiding completely in the face, here you will lose 100%. So if someone says, I have a robust, very robust face recognition algorithm which can recognize a person even if you hide everything, it means he is lying. Okay? He is lying. Except in some situations, even if we can imagine this guy, Yeah, now we can say he's lying, but he is lying if he is using traditional cameras. Okay, hide your face, and even with 3D, what I will see just something like this. It doesn't mean with 3D you can solve all problems. I'm not talking about... Yes, this is what I mean. If you change maybe the camera, you use something different, here maybe you can solve some problems. Thermal cameras, yeah, maybe with thermal cameras you can see just the distribution of the heat on the face, okay? It doesn't mean you can solve everything and you can recognize really the person. But using a simple traditional camera, it's for sure you cannot recognize the person. Here you can in some cases, yeah, you can think about something different. But what I mean about this is just the idea with traditional cameras you cannot recognize the person. We have some studies, you know. Just a few years ago I supervised a PhD work, and it was about recognition of persons not from their face. So we have one person here. So as I said, I supervised a PhD work, and the idea wasn't to recognize the person from their face, but from their brain. Okay, from the brain, it means the idea was to access to the information of the brain. Okay, and we try to use some recognition systems, and here it wasn't with a camera. We use, in fact, MRI. Do you know what's MRI? Magnetic resonance imaging. And if you use magnetic resonance imaging, you can have in fact a 3D visualization of the head, and you can visualize the brain. You can extract in fact one slice of the brain, okay, and once you have the brain, you can extract features, and you can use them for recognition. But here we are using completely a different system, and it's not like a camera where just in real time you capture the face, and in MRI it's much more complex, okay? But using a simple camera, it's for sure you cannot do it. Okay? You have another issue when you deal with face recognition, is the spoofing issue. So I think last time, it was last year, some of you attended some talks, you know, about spoofing issue. So what can you say about spoofing in terms of in the context of face recognition? Do you remember what we saw last time? Spoofing. What is spoofing?
Trying to police the system by providing misleading information to the system, or
So the idea is to try to attack a system if we consider one face recognition system unrolled to be used with a certain number of persons. Okay, so just imagine we have 10 persons that are allowed to use the system. They have been enrolled, and this person is not enrolled in the system, but this person is enrolled. So this guy tries to spoof the system, to attack the system, okay, because he knows that this person is allowed, so he tries to use a simple photo of an authorized person, and with some hopes, you know, I think maybe he can attack system. In some cases it works, okay, in some cases for sure it works, and you can even use it in some basic face recognition systems. You can print a photo of someone and you can show it to the camera and you can access to the system. Why? Because the system is not sensitive, you know, to the environment. The system will not analyze different parameters to make the difference if the provided information is real or fake. So this is the idea. Once you capture an image, okay, so your face recognition system, if it's a basic one, he will just directly try to capture or to extract features from the face, and he will use classification or verification method. Okay, so if the system is not sensitive, if it's not equipped by an anti-spoofing, probably, yeah, he can accept what you present to him. Otherwise, your system may be equipped by an anti-spoofing system. And here, the idea is you have to sort your data to say, is the data real or fake? Okay, so this is your system should, before processing the data, the first thing the systems should at least achieve a verification to say, is it real or fake? If it's real, the system can proceed for recognition. So you can extract features, you can check the database, you can do many things. But if from the beginning and after some operations you say, oh no, it looks like a fake information here, you stop everything. Okay, so if we look at this one here, it's a spoofing in 2D because this person just printed a photo, so it's 2D. And this one, this guy tries to spoof the system using 3D mask. Okay, so if we take just this one, 2D, it's for sure it's simple, you know, to print the photo of someone. So if I ask you to develop a system and I tell you just try to make it robust, or try to find a way to detect if the face is real or fake in the case of 2D. What can you do in such a case? What can you propose as solution?
Maybe you can tell the person to rotate a little bit the face to detect if there is.
Okay, here, so you want to supervise and you want to control, right? You want to control because you want to interact with the user.
Yeah, just like you said.
Yes, you will tell him, okay, move your head, do this, do this. Yeah, we can ask him blink the eyes, do this, do this. Okay. So if he is presenting a photo, maybe it will be difficult for him, except if he has many versions. And each time you say, okay, smile, he will say, okay, I will smile, and he will just pick another photo with with smiling. But here it's a controlled situation, so you have to interact and you have to ask questions to the person. What can you propose as another solution?
Maybe to use a 3D camera.
You can use, yeah, if you want, a 3D camera. Yeah, okay, so here, look, controlled situation. So you make the enrollment or, the test interactive. We can use 3D camera. Why 3D camera?
A model of the face.
Because in fact, if you present, if you use a 2D image in front of a 3D camera, you cannot extract the depth.
Yeah.
Okay? You cannot get the depth from a 2D image. Okay, what else? So we have control situation, 3D camera. Yes, Hassan, you said multi-spectrum camera. Okay, good. What can you propose as another solution?
We could do advanced image processing, extracting features from the image in order to distinguish between fake and real image. Because certainly there will be some differences, but we need to do more advanced image processing.
Yeah, when you say advanced image processing on the image, so as like what?
Shadow analysis and
texture. Maybe we can analyze the texture. So here, this is a photo. You take a texture here, okay, and you try to analyze it because you will analyze the texture from paper.
So if the system can make difference between a real photo.
Why not? It depends on the algorithm that you develop. So you have to analyze. You should be able to analyze, some regions, but by extracting some features, because this is just paper. We don't know what is the quality of the paper used. Okay, so the texture maybe will not be the same. So you can analyze the texture. What else? Texture. All these are just solutions, but sometimes you can combine them. Okay, there's no perfect solution, but you can think about this. What can we propose? Some people, they can analyze the background. The background. when you are in front of the camera, you know, you are not stable at 100%, you know, and you can in fact analyze some movements, and you can see if, you know, there are some, even you can analyze the background of the person here, because normally if you are moving a little, just a little, the background is supposed to be stable. But if you are using a photo, you take the photo, you move a little bit, your background will move with you. And here you can say, this is not normal, right? For example, when I say the background, imagine there is a, I don't know, a chair just behind you. If it's real, your head will move a little bit, but the chair is not supposed to move. But if you are using a photo, we can say, yeah, the photo and the chair will move.
So it's kind of controlled environment. You have to show background.
Yeah, but maybe it's easier. It's not like when you interact with the user, the guy is happy and you tell him, hey guy, don't smile. Do you imagine, you know, it's not, in some controlled situations, it's not very, you know, it's not flexible, it's not a very comfortable situation. People, they don't like when it's very controlled like this, because they are a little bit, it's maybe scary, you know, in some cases. Yes, because they will think, yeah, what they will do and what they are doing and why they ask me, don't do this, don't do this. It's not like, you know, if we make a system very, I would like to say, friendly, flexible, you know, you are very normal, comfortable, you look at the camera and you say, okay, yes, you are allowed to access to it. But in some cases, yeah, it's a little bit difficult. So, as I said here, yeah, you can analyze the background. What else? What can we do? So, background. You see, so far we have 5 solutions, and you can even invent other solutions. Yes, Uttara says, try to detect occlusion. Color, the color of what? Occlusion of what? I don't know if it's a new question, or maybe he asked a question. Uttara, can you occlusion behind? I didn't understand what you mean by behind the face. No, occlusion, when we talk about occlusion, everything which may hide your face, we call this occlusion. We cannot say an occlusion behind the face. This is not occlusion. Okay? If we can see, yeah, maybe the chair is occluded by the face, but we don't want to detect the face. We don't want to recognize the face. The chair. We want to recognize faces. So don't talk about occlusion behind the face, okay? Because the region of interest is here. Yeah, okay, here you can say we can use the infrared, but we talked about multi-spectrum camera, so it includes this solution. Infrared, you know, it's one of the solutions that may be included in multi-spectrum camera. And ultrasound sensor, how can you use the ultrasound? How can you use the ultrasound? So this is a question. It may, you know, if you use ultrasound, you may use it, in fact, to estimate the depth. You can use it, in fact, for the depth. This is what you can do. So it's also is one of the solutions of 3D camera. Okay? Why? Because, you know, do you know how ultrasound work, you know? For example, this is a face. Okay, and imagine I want to use ultrasound system. So ultrasound, you know, you send a signal and you will get an echo. Okay, and this echo will be recorded by your system. So, for example, the echo of the tip of the nose here, you can, in fact, we can measure the distance between the ultrasound and the tip of the nose, and we can also, you know, measure all these distances. Okay, but here if you use a mask, you will have the same solutions, and it will not work. So sometimes, in some cases, you have to combine. So it depends on the system that you want to develop. If the system is very cheap, very basic, so you can use any face analysis or recognition algorithm, and it's okay. But if you want to, you know, the application is very sensitive, here it's very important your system should integrate an anti-spoofing. So just for people who didn't attend the class about spoofing last year, there are links. So Hassan, maybe you can send them links of videos. Okay. So in fact, yeah, we have in fact two. The second link is on evaluation. You can send them to both links. Okay. Okay. So you will receive two links. Yeah. And it's in YouTube, and this is what we did last time. We recorded, in fact, a class. We invited two people who presented or they delivered the course about spoofing. When you have time, try to have a look on the video. It's around 3 hours. Okay, so it has been recorded here in the university, and it's like what we did in fact this year. Probably you will receive another video, because last time, I think 2 weeks ago, we invited someone from Ireland. And he delivered a class, and the class was recorded, and it will be maybe in YouTube, and we will send to you a link. Okay. So try to have a look on this classes about spoofing, anti-spoofing, and so on. So, do you have another solution to propose? So we saw so far 1, 2, 3, 4, 5 solutions. Can you propose another solution, just to detect if the face is real or not real, if it's fake? No other solution?
Maybe a zoom of the camera to say if there is a difference between two backgrounds.
You zoom?
Zoom out.
Yes.
Zoom out and see if there is a difference between the backgrounds.
Yeah. Here something that shows a version of what's going, and when you try to put the face inside the frame,
Yes.
and in the background you see the bigger image, the outer frame of the image, and you see if he is trying to do something like put a frame in a frame or something.
Yeah. It maybe, yeah, it depends on the distance, you know, between the camera and, because sometimes even if you zoom out, you cannot see the background if you are too close, you know, except if you use another camera behind and to see if the person is normal or not normal, or if it's, yeah, they are using something else. Anyway, but we can imagine something else. For example, I don't know if there are some studies about this or not, is to analyze eyes movements. Eyes movements. You know, I don't know if they published something on this. If in fact, normally, if you ask someone to look at special light or spot, okay, spot light, and just you ask someone to look at the spot, you know, it's not that easy to be very stable. You know, if you record the movement of the eyes, you can notice something. You can have, you know, some signals like this. Why? Because eyes is always moving. It's always moving. So some people, they can try to analyze signals like this. Sometimes we have what we call saccades. Okay? So if it's a photo, probably it will not move. And even if it is moving because the person who is holding the photo is moving, the signal is not the same. So if you model this signal and you model this signal, you can see some differences. Okay? And you can think about something else, Hassan, what you did last time.
Make maybe a spot and change the light.
Yes, exactly. Except if you create a system to react to the light. So each time, you know, you can propose one solution, and you can find a solution. But the idea is to make the solution very difficult to spoof. This is the idea. So you have to make anti-spoofing or the spoofing difficult task. Do you have questions? And what you have to understand that currently people working in face recognition, I think, I don't know, more than 50% of people working in face recognition are working in anti-spoofing systems. Why? Because they said if everything is okay, no problem, we can recognize the person. But the main issue is if someone tries to attack the system, and that's why a lot of people are working in this field.
There is competition, actually.
Exactly, there are competitions even for spoofing, anti-spoofing, because it's very important, you know. Do you have questions? No question? Yeah, look at this slide. Do you know these persons? Celine Dion and her husband. Okay. So you don't see two of them? So two of them are real and two others are fake. This one is fake? This one?
No, the right one is not fake. The
Right is right.
Right, my right or?
right.
It's my right. This one is real?
Yeah.
This one? Real? Real? So you think here they are real and
No, maybe
maybe? If there is maybe, it means that you're... So, yeah, Nietzsche said that two in the middle are fake. And this is true. Not maybe, they are. This is true. They are fake. What?
we cannot see where from here.
That's why.
This is the elimination problem. Yeah. We call this the perception. We call this perception. Okay. Here they are fake, and here it's made by wax. You know what's wax? Yes. Yeah. You can see this in Paris. It's at Musée Grévin. I don't know in England. Maybe Nietzsche can. Madame Tussaud, I think. Madame Tussaud. I don't know if there are, if we can find Céline Dion or not. Here in Paris, we have Musée Grévin. In the UK, they have Madame Tussaud. And in the US, also Madame Tussaud. So you can find, personalities like this. I don't remember in the UK, because I went there, but I don't remember if I saw Céline Dion there. Anyway, so the idea is that we can make, we can design, if you want, a 3D face which looks like approximately exactly like the real one. So this is not a big challenge. We can. So do you imagine if you want to attack a system with faces like this in 3D? So even if you use a 3D camera, you have all the features. If you extract features from this face, it will be the same. So that's why here probably the 3D will not be 3D camera will not be the solution. So you have to use another solution. Maybe you have to use multispectrum camera. Maybe you have to analyze movements just to make the difference. So here the idea is to say 3D is good, but now we can design any face in 3D easily. And if you noticed, in the previous slide, this one, there are some websites, they can create masks like this in 3D just you send your photo and pardon,
Profile photo
and even profile, yeah, and they design for you a 3D mask like this one. Okay, so it's not complicated to have something in 3D, but it's for sure if you are using some sensors to analyze the texture here and here, so you may find some differences. Okay?
We see in the lecture that they were making one fake data, which was
Pardon?
they were making a data with fake 3D images, 3D maps.
I didn't understand the question. Sorry.
They were just putting in a data 3D masks, and they were comparing with the real one.
In which case? Are you talking about this one?
In lecture, I can remember something they were putting
Yes.
Data.
Yeah, for sure. But it depends on what you call data. Because if the data are related to the shape, it's something. If the data are related to the texture, it's something else. If the data are related to the movement, it's something else. You know, because you can also integrate movements here. So that's why everything depends on your algorithm.
No, they were putting one data in anti-spoofing system, and it was comparing with 3D masks and all the things.
Yes, for sure. You know, all the systems.
We can use this also.
We can use this, yeah, of course, because you have to compare. Each time you develop something, it's compare. Okay, it works like this. But you know, you don't have here. I cannot give you. You know, I cannot say what is the perfect solution, but just you can think about the different solutions. Okay, good. So when we talk about face recognition, you have to understand there are some algorithms, you know, for face recognition, and we can even classify methods or approaches of face recognition. So we have what we call 2D global approaches for face recognition, and we have what we call 2D local approaches for face recognition. And you have the same solutions, you can find them for 3D. So the thing which is important for you is to make the difference between what we call global approach and what we call local approach. When we talk about global approach, I don't know if I will see. Okay, so do you know this person? Yes. He was my former student. Yeah, now he's working in a company and since a few years. Yeah, it's him. Pardon?
So they have good face recognition.
Yes. Yeah, because at that time, all students, I asked them to create a face recognition system, and they captured their faces. You know, it was here, just in front this wall. You see, it was just here. and we use the camera and so on. So they created their own database, and they tried to work on some algorithms. Okay, so here, when we talk about global approaches, it means the input of your system will be an image. Okay, in this image you have a face for sure, but the idea is not to extract some or to measure some information from the face. We don't extract the face, we don't extract eyes or nose or something like this. The input is the whole image. It is what it is. That's all. So when you say global approach, it's like it's blind. It's something global. The input will be one image. So the idea is to extract some features from the image as global information. You cannot make a difference. You say, oh, yeah, this is eyes, nose, mouth. No. You discard completely this information, and this is the challenge, is to try to extract features, some global information from this image. And you can have a lot of parameters. And it's about feature extraction. Okay? So we call this global approach. Local approach is different, you know. Local approach, you need to extract some specific information from each image. Yeah, this is just. Do you know these images? Who is this person? Do you recognize? Yeah, Margaret Thatcher. Do you know her? No? Some of you, it depends on the age of persons, I guess. She's not too old. Yeah, she's not too old, but yeah. I don't know if she's Margaret Thatcher. She's not alive now, I think, Margaret Thatcher, yeah. Nitsa, she was dead, yeah, since, I think, 2013? Yeah, 3 years, yeah, that's why yeah, she's, yeah, recently, 3 years. Okay, good. Yeah, I show you this slide because that's why I said, can you recognize this person? Okay, so maybe you can say, yes, we can recognize the person, maybe because she's known for some people. But it's about perception, you know. The problem is that if we rotate, okay, if you rotate the image, what do you notice? What do you notice? If before it was like this, no one says that there's something wrong. And when we rotate it, and you see, all it's about perception. Our brain, how our brain recognizes faces. So you have to understand the way we recognize faces is different than what the computer can do. For computers, we think about algorithms, feature extraction. For human being, when you meet someone and you recognize him, you never extract features, right? You never says, let me just measure distance between your eyes, distance between, I don't know. Never you do this, right? Even a child can recognize anyone. Hopefully he can recognize his father, his mother, and never says, yes, I'm expert in biometrics, let me just extract some features and I will compare with my database.
And I'll use the 3D camera.
Yeah, or maybe, yeah, something like this. So you understand that perception, the brain, the way we recognize everything is completely different than the methods that are used by computers. So sometimes we think like human being, and sometimes we have to think like a computer. And when you think like a computer, you can talk about feature extraction and things like that. So do you imagine here something like this? If I show to you these two faces, maybe you can recognize this face, but this one you say, no, I don't know, who is this person? Okay? Why? Because your brain maybe was trained to recognize some specific faces. And you can do the same exercise. You take your photo, picture of, yeah, just you cut here, you cut eyes, nose, and you rotate them. You can create something like this. And try to see if you can recognize yourself or not. I don't know. Or maybe you can show the photo to someone you know and ask him if he can recognize the person. So our brain is trained, you know, to recognize faces differently, and it's not that easy, you know, to train the computer to do exactly the same like our brain. That's why we process data differently. The information is processed completely, differently. Yeah, here. When you see this person, yeah, it looks like the same person, right? If we rotate it, you can notice that, yeah. And here, if you extract features, you know, if you use some features, it will not be the same. So maybe here the face recognition system will says no, two different persons, okay? Or maybe the system will says no, they are the same. It depends on your algorithm. It depends on the features that you extract. But for human being, probably you say no, two persons completely different. If you meet someone like this and someone like this, you will say no, they are not the same. But if we rotate them, maybe you think that they are the same. And here you have the perception, which is different than you know, mathematical calculation, especially when we think about feature extraction. Okay. Now we have to move to something which requires mathematics. Even if I have some, yeah, I have to send to you the original slides, because in the system I noticed, yeah, we have some characters appearing here. It's not normal, it should be like this. Okay, so don't pay attention to this problem. In fact, here we want to show just how to say a vector. So before we talked about global approaches and local approaches. Global approaches, I said the input is an image. You don't care what is this image. Just you try to analyze it and you try to extract features from this image. Okay? And you have the local approaches. Local approaches here, yes, you need to do some measurements. You have to extract some, you have to measure, you extract some landmarks from the face, and you have to do some measurements. Okay? So now we will start working on global approaches. Okay, global approaches, especially using the PCA as one famous method in face recognition. Okay, so we will try to see some equations, some mathematics and things like that. Okay, that's why I prefer to give you a break, and just after this it becomes much more theory than practice. I know you like theory a lot. I know you like mathematics. So, but it's very important, you know, it's very important because nothing will work without mathematics, but at least the idea is to show you how really face recognition work. Okay? So we take a break and we come back in around 15 minutes. Okay? Can you hear me? Yes? Yeah, does it work? Yeah, okay, good, thank you. So, I said that now we try to discuss a little bit about some methods, especially we try to discuss about global approaches, and specifically we need to discuss about something very important called principal component analysis. This method of principal component analysis is used very often for face recognition using global approaches, but it can be used in image processing, signal processing, or other applications to solve many problems, in many applications. It's something well known. The PCA, it's something known. That's why it's important to understand how it works, how we can use it, and after this, how we can use it as an application for face recognition. So you cannot say the PCA is something just specific for face recognition. No, PCA is a data analysis tool, okay, used to solve many problems, including face recognition. Okay, so to start, just let's see this slide. As I told you, yeah, I will try to give you the original slides, because here you notice that we have some issues, you know, here with some symbols. It should be like this. Okay, so look at this slide, and we start by saying let an n by 1 observed signal defined by like this. So we observe one signal, okay, x, we call it x, and this signal contains the following samples from x1 until xn minus 1. In fact, you have n samples. It starts from 0 until n minus 1, and the vector is n by 1, which means n rows and 1 column, okay, n by 1. So now we consider another signal y, called y, which is obtained by transforming the signal x, okay, the signal that we observe, through an n by n unitary transformation matrix called A. In fact, it's like I have the vector x, and I will transform it by matrix A, and the output will be y. So I know the dimension of x is n by 1. The dimension of A is n by n, okay, and this is what we try to see how we can manage this. How can we convert this vector x through the matrix A, okay, to obtain a matrix y, and normally we should get at the end a vector n by 1. It's not about multiplying directly, you know, x by a, but look at the transform or transformation will be like this. Y equals A transpose. So A transpose by x. Okay? This is the transformation. And A transpose.
Y by n. 1 by n.
Pardon?
1 by n, yeah?
1 by n. Just I want to define, you know, the unitary matrix. You know, the unitary matrix. We say that the matrix is unitary if you have the inverse of A equals A transpose. Okay, so this is the definition. This is what you have to understand. And A here, the system, is unitary. So we can apply this. A inverse of A equals A transform. So if you have something like this, Y equals, okay, A transpose X. So if we multiply both sides by A, what will happen? If we multiply both sides by A, let me, can I change the color? Excuse me, I cannot do it. I wanted to, excuse me. Okay, I wanted to change the color, but there's something wrong. Okay, I cannot do it. Okay, so we said if we multiply both sides by A here, and A here.
A here will come. We cancel with A transpose.
Yes, so here A transpose is A inverse of A. So X equals A multiplied by Y. Okay? So look here, the structure of the matrix A. Okay? The structure of the matrix A is like this: A0, A1 until A minus An minus 1. And you can notice that A here is bold, which means A is a vector. Okay? I will just I hear there's a singer just out. He's happy. Okay, let me close all these windows. I close this. Okay. And the last one. And it will be so. Matrix A equals, you know, A0, A1 until An minus 1, and in fact all these A are vectors. It means A, it's like this. You have a vector here. This is A0, this is A1 until An minus 1. And we call these vectors basis of the matrix A. Okay, so the structure of A, that's why when you see a matrix like this, you know, here because it's bold, so it means you have a vector. It's a column vector like this. A column vector here and column vector. Okay? So this is the idea. The idea is that I observe something and we transform it using this spatial matrix. And we said that it's a unitary transformation matrix. It's spatial. Because why it's spatial? We said that the inverse of A equals A transpose. Okay. So, yes, we calculated X. We found that X equals A Y. We saw how we found this. Just by multiplying both sides by A, we can obtain this. It means the observation you observe something, it's a kind of linear combination. This is not a, because it's just a problem of equation, it should be sigma, okay, sum. Replace it by sum. Okay, your matrix A is like this, which contains vectors. Okay, and you have the vector y, like this. So the observation x is in fact A multiply y, which is just linear combination of this basis. Imagine if y equals, I don't know, a0, a1 until an minus 1. What you will obtain if you multiply this matrix by this vector, you will obtain, tell me, a0 multiplied by y0 plus, yeah, a1 plus n minus 1 multiplied by, okay? So you see, it's and all these are vectors. It's combination of linear combination of vectors. Okay, let me write it like this. X, I will write it like this. X equals a0 multiply y0. This is 1, 1 until n minus 1. So you see here, you have vector, 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 and the signal that you observe is a linear combination of these vectors. Is it clear for the moment? We didn't do something very complex. We observed an x vector. We transform it using the matrix A. This matrix A is special. We know that A inverse of A equals A transpose. That's why, since this matrix is special, we can express the observation X as a linear combination of vectors A. We can do this just because A is a unitary transformation matrix. Okay? Good. So we have the relation between X and Y through the transformation matrix. Yeah, we have still some symbols problem. And now we try to define, the principal component analysis. Sometimes it's well known to be Calhoun-Loewe transform. Calhoun-Loewe transform. Some people they say Calhoun-Loewe transform. Some people they say principal component analysis. And I would like to say that the PCA it's much more used than Calhoun-Loewe transform. Okay? So we try to follow step by step the idea behind the Calhoun-Loewe transform or the PCA to understand how we can deal with the transform. So the first thing, read this part. Calhoun-Loewe transform can be used first for dimensionality reduction, and second to decorrelate the observed data. So we have two advantages by using this transform. First, we can reduce dimensionality of data. What can we give as an example of dimension reduction? if sometimes, you know, you have data in dimension 3D, maybe in some cases the third dimension is not useful. In such a case, with Carhoon-Loew, yeah, you will transform it to 2D. Sometimes you have 2D information. So the Carhoon-Loew transform will reduce it to one-dimensional. In some cases, you can have n-dimensional system, and it will be reduced to n minus something. Why? Because some dimensions are not useful. So this is the first thing. And it's very important because when you reduce the dimension of any problem, it means in terms of processing it will be easier and faster.
You cannot lose some information.
Pardon?
You cannot lose some information in transformation.
This is the idea. If it has been reduced by this transform, it means some dimensions are not useful. If they are not useful, you cannot say that I lost information. Okay? Sometimes you say, okay, this is three-dimensional, but you don't see really three dimensions. You say, okay, why I have to process this data as three-dimensional? Because I see I have only two useful dimensions. The third one is not useful. So if it's discarded by Carhoon-Loew, it means really you don't need some dimensions. Okay? It's like I give you one, just paper, and you see the paper is 2D, but if you use 3D camera, maybe you say, okay, the third dimension is, yeah, especially if it's this one, the third dimension is not very important. You can use 3D camera, you can have 3D coordinates, everything. But you say, really, the main information is here. I'm not interested in the third dimension. So that's why the PCA, when you use it, whatever is the dimension, because the dimension is not just 2D or 3D, it may be ND. You have sensor, and this sensor will capture N data. So you can consider this vector as ND. But you have to understand that sometimes some dimensions they will not they are not very important. Okay, so this is the first thing. The second thing is that we say we use it to decorrelate observed data. What do we mean? Decorrelate, not correlate. Decorrelation. We have what we call correlation. Probably we saw this last year. Correlation. Something is correlated to something else. But here we want to decorrelate.
What is the benefit from decorrelate?
Yes. Look, I will give you an example. Let me thinking about the example I will give to you. I will create a password. Okay? And in this password, it will be This is the code I am using. Okay? How many characters I used? I used 4. 4 characters. So this is your password. So the idea is that the question, do you think that these values are correlated to each other or not?
Yeah. Each one is plus 2 of this one.
Plus 2. Okay. So it means since this one is correlated with this one. Why? Because if I have this information plus 2, I will get this information. If I have this one plus 2, I will get this one. And I can get this one too. So in fact, I don't need, this is a password with 3 values. So in fact, since we have correlations here, if I can access only to the first one, it's finished for you. I can find the password. Why? Because there is a kind of rule. I can predict the other values. I can predict. If I can predict, it means it's correlated. I have just using this value 2, I can predict the next one 4, I can predict the next one 6, and I can predict the last one 8. So even if you use something very complex with 100 values, imagine 2, 4, 6, 8, 10, 12, 14, and you say, look, I have created a very complex password, very complex, and you are proud to use very complex, and you think that no one will find it. But if we find just a correlation, the rule you used, so just using one value, we can predict all the password. Why? Because there is a correlation. Okay, there is correlation between values. That's why if we find a way to modify this word and to decorrelate the values, it will be much more interesting, much more useful. At least, maybe, look, if we have 100 values here, maybe after decorrelation, we can reduce, not this one, for this one, if we use decorrelation, we will find just one value. Because all values are connected to each other. But imagine for you, just you will invent a password, a set of values, without thinking. 2, 10, 6, 5, anything. Okay? Maybe you used 1,000 values. But probably there are some correlations between some values. So when you decorrelate, you transform this vector, maybe the initial vector, which is 1,000, will be reduced to 200 maybe. So if you decorrelate, you will reduce the size of your vector. If you find some correlations, it will reduce the size of your vector. Why? Because you will suppress redundancy. Okay, everything which is redundant, you will suppress it. And we will see an example about this. Okay? So what you have to understand so far, that when you use this transform, you can use it in fact to reduce the dimension. If you have a lot of data undimensional, you can reduce the dimension. So the dimension is reduced. Okay? So if you want to process the data, it will be faster. Why? Because you reduce the dimension. The second thing, you will reduce also the data because you will discard all correlated data. Okay, you are sure, you know, decorrelated data, you obtain decorrelated data if you cannot predict one value from another one. Okay? If I have one value and I cannot predict the next one, it means they are decorrelated. But if you can predict it, it means they are correlated. And if they are correlated, it's like, it's not useful, because if you can predict.
Which is the vector when values are correlated?
No, in fact, at the beginning you have one vector x. Values are correlated, values are the dimension and anything, any dimension at the beginning x. This is what you observe. At the beginning, your vector x is not processed. So the dimension can anything. And maybe the values in this vector are correlated. Yeah, maybe. Maybe not. But maybe, because when you measure data, you capture data, maybe sometimes you don't think about if this thing is correlated with this one, this thing is correlated with this one. So that's why you said, just I will capture data, and you will have a vector, a big vector. And you say, okay, are all values in this vector useful? This is the question. Are all values in my vector useful? So, to answer, you can use the PCA. If they are all useful, you will, at the end, you will obtain exactly the same number. If the method finds that some values are correlated to other values, your vector size will be reduced. Yeah, shrink if you want. Okay? You have to understand sometimes when we use sensors, when you use sensors, when you use you capture something special. Just you capture data and you have to process all this data. But sometimes, you know, you don't think about what you captured. That's why, as pre-processing, and very often we use this for pre-processing, we say, let's reduce the data. Let's see if we have some correlated data. And we make, at the end, the vector smaller. Because when you get a smaller vector, it's easier to process. Okay? So, what is the benefit if you capture 4 information, you use 4 sensors, and you will notice that all values are connected to each other. You say, finally, if I use just one sensor, I can predict all the other values. So I don't have to use 4 sensors. So this is the purpose of this transform. And we will see some examples how we can reduce the dimension and how we can decorrelate data. Think about the decorrelation in terms of prediction. When data are correlated, you can predict. When data are not correlated, you cannot predict. It's like, do you remember the white noise? White noise. Do you remember what's the white noise? Normally we saw this last year. White noise. You have a random signal called white noise, and here you have different samples. I'm sure we talked about this. you have different samples of your white noise, and you say why it is white.
So the distribution of the samples are predictable?
Because if you take any sample, for example, this one is 9, and the next one is, I don't know, maybe 5, it's impossible from 9 to predict the value 9. You don't know. Because in white noise, any value can appear randomly. Any value, it's possible. Okay? So there is no rule between samples, no correlation. So I cannot do a prediction. Imagine the temperature signal is a white noise. I say, just imagine temperature signal. Imagine if it was a white noise. Maybe today is 10 degrees. Tomorrow you will find it -5. After tomorrow it will be 40 degrees. After this it will be 5 degrees, and so on. And you say, I cannot understand how it is changed. I cannot predict. But it's not the case, because the temperature is not white noise, so we can do some prediction. We can expect if the temperature is increasing, decreasing. Why? Because there are some correlations. Okay? The same, for example, if you take some exams for one student. So first exam, this person obtained 10. After this, obtained 2. After this, 20. After this, 1. After this, I don't know, 1. 16. And really you cannot understand how he works. You cannot say if he is good or not good or bad. You know, sometimes students, we can expect to say, yes, this guy is in the average. Yeah, we have an idea about the level, because it's something normal. But imagine someone you cannot predict his results. 20, 1, 2, 10, 16, 15, 1, 0, and you say, I cannot say which mark he will obtain next time. And here you cannot predict. Why? Data are decorrelated. Okay? When they are correlated, you can predict. So, okay, so two important information here. There are two important information, and we will see how it will work. So the first thing, we have to we calculate what we call the correlation matrix. We call it RY. Okay, so we transformed our signal X, we obtained the signal Y, and from this signal Y we calculate what we call correlation matrix. And the correlation matrix is calculated using this definition. So except these things that are not clear, we can make it clear like this. It should be Y and Y transpose. Okay? What is E? E? Do you remember? It's used in statistics, expectation. It's like the average. In statistics, the average. E. Espérance mathématique in French for some students. Have you heard about this? Okay, expectation, yeah, in statistic we can use E, Y transpose. If you replace Y by A transpose X, what you will find at the end, you will find this result. Let me, I try to, I don't know if I cannot. Okay, just I want to remove some parts. Okay, but yeah, anyway. So, do you understand the idea? Is that the correlation matrix RY equals at the end A transpose RXA. Okay? I have just a problem with the board. I cannot use my, it's not working. Yeah, no, it's okay. No, it's okay. And even the color, I cannot change it. Okay, strange. Anyway, I said the correlation matrix of the output signal equals to A transpose by the correlation matrix of the input signal X multiplied by A. Okay, so now at the beginning we had the relationship between the input and the output signals, Y equals A transpose X. Now we have the relation between the correlation matrix of the output and the correlation matrix of the input. Okay? So, yeah, still just we try to modify. Here you replace it this by sigma, and here it should be the like this. And here it's the identity, matrix. Okay, so read this sentence, and also start you can start from here. The matrix Rx can be estimated as follows. Rx is the correlation matrix of the input signal. The signal X, it's the signal that you observe. Okay? The signal X is the signal that you capture, the signal that you observe. So you can calculate Rx, which is the correlation matrix of X. It is estimated using this equation. As I told you, I will give you the original slides. It's more, yeah, because here we have a problem of samples. But it's easy to understand. It's sigma xk transpose, and you divide by n. Okay? So we estimate the correlation matrix like this, and look at what we say here. Rx is a symmetrical matrix. Then the eigenvectors are mutually orthogonal. This is definition. This is definition. If Rx is symmetric, so the eigenvectors of this matrix should be orthogonal. So they can create basis. And we say that Rx is estimating using some common techniques from the observed input signal. It means I observe X, I can estimate the correlation matrix using this equation. If you record one signal like this, you call it X, be sure that it's easy to estimate the correlation matrix Rx. How? Just you use this equation. Okay? Now, look at this. Note that if the columns of the matrix A, so this is very special case. If the columns of the matrix A are chosen to be the eigenvectors of Rx, then Ry is diagonal matrix. To understand, you have to read it again. If we have some, in special cases, A, you know, because A is a matrix, okay? It's a matrix. But if you choose to put in this matrix eigenvectors of what? Of the matrix Rx that you calculated, because you know how to calculate it. Here, the theory says that the correlation matrix of the observed is diagonal. If it's diagonal, it means the data of Y are decorrelated, because diagonal matrices for correlations, it means data are decorrelated. You have to understand. Look, I will tell you something. I take any signal. I give you one signal. I call it X. If you calculate the correlation matrix, you will find values here, you will find values here, here. Okay? If the values here are not zero, it means data are correlated. Data here are correlated if it's not zero. If, however, I give you another signal and you calculate its correlation matrix and you find that it's diagonal, it means you have values here, but you have zero here, okay? What does it mean? It means that, yeah, values are decorrelated. So always the reference will be these matrices, correlation matrices, R, X, R, Y. So in our case, what we did, we took this signal X, which is the data are correlated. We transformed this vector through the matrix A, but this matrix A is special because we selected, you know, for this matrix A, the columns of this matrix are in fact the how to say, the eigenvectors of the correlation matrix of the signal X. So if you do this, be sure the theory says we can prove that the result that you will obtain has a matrix like this, which is diagonal, which means values are decorrelated. So the input, you have correlated data, the output, decorrelated data. So you have to imagine it's like a black box. I have one input, one transformation, and one output. The input data are correlated, the output the data are not correlated, they are decorrelated. And when we can obtain this result, if you choose properly your matrix A, your transform matrix A. If you select properly the matrix A, you can obtain this result. How to select the matrix A? So calculate eigenvectors of the correlation matrix of X and use them in this matrix. If you do this, mathematically we can prove that the result will provide decorrelated data. Because it has been already proved, so you don't need really to do all the proofs, but it's like this. If you select, as we said, if the columns of matrix A are chosen to be the eigenvectors of Rx, then the correlation matrix of the output Y is diagonal, and it will be something like this. Okay? Diagonal, and you see you have zeros in this part, and you have all this part are zeros. So you have only this diagonal part which is different than 0. So far what we did, just we transformed our data. You have input data, output data. We know how to transform, X to Y. But in some special cases, if you select properly the matrix A, you can obtain something decorrelated. Is it clear? So it doesn't mean each time I take my signal X, I will use a transform A. It means that the output is decorrelated. This is not true.
So, to select our matrix A, we have to calculate eigenvectors.
Yes. To select the matrix A, what you have to do, you have you know all the samples of your signal, right? What you can do with the samples, you can calculate Rx using the equation I gave. Okay? Once you have this matrix, you can obtain eigenvalues. Okay? And even in MATLAB you have a function eigen like this. In MATLAB you can use the function eig for eigen, and you will obtain eigenvalues. So you take these eigenvalues and you use them as columns of your matrix. You see, you start from X. From X you estimate Rx. From Rx you obtain eigenvectors. Eigenvectors you obtain A. Is this scenario clear? The beginning X. From X I obtain Rx. From Rx I obtain eigenvectors. Once I have the eigenvectors, I obtain A. Okay? And after this, I will transform my signal using a system with A, and I will obtain Y. Do you see this scenario? I start from this one, like this, like this. I obtain A.
A is a matrix.
A is a matrix, of course.
And Y.
Y is the output vector. Yes. Here you have correlated data, and here you have decorrelated data. So the correlation function of this one, if you try to calculate the correlation function, you will find it's a Dirac. Do you remember? Dirac, like this. You have all just zeros here. But if you calculate the correlation function, not matrix function, of X, you will obtain something maybe like this. When I see correlation function like this, it means data are correlated to each other. There's correlation between this one and this one, this one and this one. But if data are decorrelated, you will have Dirac. It means each sample is correlated with itself. This is what it means. Each sample is correlated with itself.
So starting from Y, if we have the correlation matrix, we can go back to X.
We can in fact correlate data. If you filter your signal Y, your data will yes, you can correlate the data because it's easier, you know, to create correlation between data. But sometimes it's difficult to decorrelate the data. So that's why, as I said, if you have a password of 1,000 values and all values are correlated to each other, maybe in fact you don't need to work with all these 1,000 values. And they are not useful because they are correlated. So you try to modify these values. Okay, as I said, example, if you have 2, 4, 6, 8, 10 and so on, values are correlated. So if you use this method, you will modify the values. It will, I don't know, it becomes something like this, I don't know, something like this. And the data will be decorrelated. It means you cannot predict this value from this value. You cannot predict this one from this one, or this one from this one. And here it's more interesting. In some applications, of course. Okay? So, let's see this example. We take 100 samples and we have 2 variables per sample. Okay? Time and value. Each sample, if I select any one, you know, you have 2 variables, the time and a value. So this sample, we say, this sample is 2-dimensional. We are in front of 2-dimensional situation because each sample has 2 values. So here it's 2D, 2-dimensional. Okay? And here what we plot 100 samples. So from this example, if you try to calculate the eigenvectors, since your the example, this application is b-dimensional, is 2D, if you calculate eigenvectors, you will find 2 eigenvectors. You will find 2 eigenvectors. You will find the first one, which is here. And you will have the second one here. So what can you notice? Here it's a very important example because it will explain to you what are the eigenvectors. You should be able to understand easily the idea behind eigenvectors. So tell me, what do you notice? You have 2 eigenvectors. One is bigger than another one, all right? But at the same time, you can notice something. The first eigenvector is oriented to the direction of the cloud. You know, we can see we have a cloud of points here, and this eigenvector will show you the direction of, you know, the main orientation of your data. Eigenvectors, if you have a cloud of data, mainly they can be used to have an idea about orientations of data. So we can notice something. You have the main orientation. You agree with me? Why? Because data are, you know, distributed in this direction. But we can also notice that you have a distribution in the second dimension. That's why you have another eigenvector, but this one is smaller. Why? This one is smaller because you can notice that fluctuations of data are very limited, right? Yes or no? Let me delete it again. Okay, again. So think in terms of cloud. You have this cloud of points. The first eigenvector will give you the direction of the main points. The second one will give you the direction, you know, in the second dimension. So eigenvectors are used to estimate, in fact, orientations of your data. Here is 2D. I have 2 dimensions. So I should have 2 eigenvectors. The first one will show you this main direction, and you can see the length is more important than this one. And this is logical, but because in this direction you can notice that fluctuations are small. Okay? In this direction. But in the other direction, you know, orientation is much more interesting. So, oh my God. Eigenvectors here are important, and you have absolutely, using some examples, you have to understand the idea of eigenvectors. So, since the eigenvectors will give you a direction of clouds, let's imagine something in 3D. I will try to do it. And just maybe I can imagine I have a cloud of points in 3D. Okay, you have X, Y, and Z. Okay, and you have a cloud of points. This example is 3-dimensional. The dimension is 3. Okay, if you calculate eigenvectors, you will find 3 eigenvectors. You will probably find one eigenvector in one direction, where it's the main information. You will find one in this direction and another one in the other direction. Okay, so maybe this one will be more important. Why? Because the cloud here, yeah, longer. And you will have the second in this direction and third one. So if you can apply it to any object, take any object, and here, I don't know, for online students, if I have to use maybe the camera. Let me turn on the camera. You can see.
You need to click enable camera.
It's enabled, no? Can you see me in the camera?
You need to
Okay. Look, now we will see what are eigenvectors. I will take just this object. Is this 1D, 2D, or 3D? 3D. Okay. Can you see eigenvectors here? It's 3D. This is 3D. So normally, I can see in this object 3 eigenvectors. You have the first eigenvector in this direction, because I have the main information in this direction. I have information in this direction, and I have information in this direction, right? So if I calculate the eigenvector, I will find one eigenvector like this. I will find a second eigenvector like this, and the third eigenvector like this. Why? Because I have information in all these directions. The main one will be this one. Why? Because I have more information here. So when I calculate the eigenvector, I will find that the eigenvalue which is associated to the eigenvector is important. And the eigenvector here, its eigenvalue will be small. Okay? If I give you another example, can you see eigenvectors here? Do you have 2 or 3? So I have the first eigenvector here. Look, if the paper is like this, the eigenvector is like this. If I rotate the paper, the eigenvector will be rotated too. So the eigenvector will give me also the rotation. I can rotate it like this, and each time, I rotate it. Why? Because it gives to me orientation of the main information. So this is the first one. The second one is like this, right? And normally it should be smaller. The eigenvalue, it should be smaller. Okay? I have less energy in this direction than in the other direction. And even if I rotate this object, I don't have another. Do you have a pen? Please give me a second pen. Maybe a small pen. No, you don't have this. No? Thank you. But normally it should be like this. Okay. We have the first eigenvector like this. The second one is like this. It's like this. In fact, it's like this. So if I rotate the object, everything will be rotated. It means that my eigenvector will give me the orientation of the object. And it can be used, if you want, to estimate the orientation of some objects. Because this paper, I can transform it to digital information, right? You can have just cloud of points. If you have cloud of points, you can do some calculations. You can have the first one, the second one, and is there a third eigenvector? Yes, I have in fact another one, the third eigenvector, but it's too thin, too small, because its eigenvalue will be very, very small. So in fact I can neglect it. Basically it was 3D. Since the eigenvalue is too small, it's not useful, and I say, okay, let's neglect the third one and let's work only with two oriented. And here I did what we call dimension reduction. We reduce the dimension. You see? Even if at the beginning you have something in 3D, but you say, okay, yeah, this one is not useful, I will reduce it and I will make it just 2D, I don't have to work with the third one, because otherwise I will do many calculations for nothing. The last one is too small, so I can neglect it, and here I reduce the size. So eigenvalues or eigenvectors, very important to estimate the orientations of objects.
The importance of
Pardon?
the importance of each
Yes.
vector.
Because when you calculate eigenvectors, they are associated to eigenvalues. If the eigenvalue is very important, it means you have very important orientation in this direction or in the other direction, so you can use it for orientation estimation if you want. Okay? Is it clear? Because very often people, they say, you can find in the books eigenvectors, eigenvalues, but you don't understand. Just you do mathematics, but you cannot, sometimes you cannot imagine. So now, take any object and you say, okay, directly I can see my eigenvectors. Okay? Any object you can imagine. If it's a 3D object, so you should have 3D vectors. Okay? I cannot say 4D object because we don't use, in mathematics we can use 4D or AND. In theory we can use it, AND. But for visualization, you can visualize 3D objects, right? And you have 3 dimensions, and you can reduce 3 to 2 or 1. So if I take this one, I don't want to, I can even transform it to 1 dimensional if I want, but I don't want to use it, I can reduce everything and it becomes just 1D. Okay, good. So here, if you look at the previous example here, this one is very important. Delete, okay. Oops, where are my slides? Good. So look at here. As I said, we have this cloud. You have the first orientation. You have the second orientation. And here, if we find, for example, because this one is associated to an eigenvalue, and eigenvalue of this vector is too small. So if we want, we can decide to neglect it if we want. Because you can neglect this one, but it's too much. But maybe it's more interesting to, if we want to approximate this cloud. In fact, we can, if we project all these points over the first vector, what we will find? Just 1 line. It becomes 1 line. Okay, so at the beginning it was a cloud of points. But I said, yeah, but variations here are not very important, are too small. So let's do a kind of approximation. So here I approximated and I transformed the 2D to 1D. Why? Because the second dimension, I said, okay, I can neglect it, it's not useful for me. I will work just with the main information. Okay? This thing is very important. Okay, all this is not just mathematics. You have to understand we have a lot of, should be, yes, like this. You have to correct. But remind me, I have to give you the original slide. And maybe it's already uploaded. I think I have uploaded the slide, so you can check for this. At least you can compare. So here, in fact, just to show you the process, the mathematical process, starting from the observed signal x. Look, you have x here, you have x signal. From x you can calculate the correlation matrix. Okay, so imagine this is the correlation matrix of my observed signal. Once I have the correlation matrix, I can calculate eigenvectors, and you can notice that eigenvectors are associated to tell me, values. Okay? So here you have eigenvector, and this one is eigenvalue. Eigenvector, eigenvalue, eigenvector, eigenvalue. So this one is A0, A1, and A2. So once I have A0, A1, and A2, I can construct my matrix A. So the signal Y, the correlated, is obtained by multiplying A by the observed signal X. Okay? So you have the first, this is A0, this is A1, and this is A2. So this is the scalar multiply, product, It's like I'm doing this, like this. I'm doing, let me just maybe, I will,
So it's not
what?
No.
It's not on the plan. Oh, okay, I can upload the original slides. Okay, so here, you see, so look, you multiply this by this one, this by this one, and this by this one, and you will obtain each time, yeah, y0.
We multiply eigenvector with eigenvalue.
Yeah, each time, you multiply this vector like this by this vector by this vector, second one, this vector by the third one. And each time if you multiply this one by this one, is the scalar product, you will obtain a scalar, one value here. When I multiply this one by the second one, I will obtain a scalar, which is the second value of y, and so on. So you can practice, you can do it. It's not complex. But here it was basically to show you the process. I start from something that I can observe, something that I can record. It may be a microphone, it may be anything. It will provide data. From this data, I can calculate the correlation matrix. Once I have the correlation matrix, I can calculate eigenvectors and eigenvalues. Once I have this, I can construct my matrix A, and I multiply x by A, and I will obtain my new output Y, and I am sure by doing this that all data will be decorrelated. Okay? And we will see next time how we can use this to solve the face recognition system. But believe me, this thing is very important. You can use it in many applications. Many applications. Even we saw one of the applications, if you have one object in 2D or 3D, you can use it to estimate the orientation of your object. Sometimes you can make your computer intelligent, and you have one object and you want to track the orientation of your object, even in real time. So what you can do, you can calculate, for example, eigenvectors if you want. It's not exact. No, it's not the same. It's not the same approach. Here, it's about really you have a cloud of points, and visually, you can see distribution of data. If you can see the distribution of data, it means mathematically you can do it. You should obtain one for this pen. I will have this eigenvector, the second one and third one, since it's circular, the two last eigenvectors will be the same, because it's, you know, this pen is circular, so it will be the second and third will be the same, but the first one is the most important. So I can imagine one application. I show any object and my system will define the orientation, you know, automatically. Any object. It can be implemented for robots, because sometimes robots, they have to estimate the orientation of some objects. So many other applications. And sometimes we can use this for registration. For example, if you have an object like this, or excuse me, you have many objects in different orientations, you say, okay, let's normalize them. Yeah, change the orientation, normalize the orientation of some objects. So you can also use this. So the idea, try to understand very well the PCA, and it's not finished, because we will see next time how we can use it